For the first session, we are honored to invite Dr. Khoa Nguyen from Nanyang Technological University, Singapore, to deliver his presentation about Introduction to Lattice-based Cryptography. Let's send him a warm welcome and a great applause.
Okay, so thank you for the introduction, and I would like to thank the organizers for arranging this event and for inviting me. It's my honor to be here in front of you. Okay, so in the two lectures, I would like to give a brief introduction about lattice-based cryptography, which is a major branch of cryptography nowadays. So, okay, so let me ask you a question. So how many of you have heard about lattice-based crypto or have experience working with lattice-based crypto before? Okay, so apparently not many of you. Okay, so don't worry, we will start with the very, very basics. So during my lectures, so please feel free to ask questions whenever you feel unclear about anything, okay? I will try to answer to your questions. If I cannot do that immediately, so we can discuss after the lectures, okay? So this is the plan of my two lectures. So first I will give a brief history of cryptography and both quantum cryptography, which is a bigger branch that contains lattice-based crypto. And then I will go to the history of development of lattice-based crypto in the last 2 decades. And then we come to the main technical part where I will review what is lattice, what is lattice problem, and how to use this to build crypto. And maybe in the second part of second lecture, so we can talk about the two hard problems that are mainly used in lattice-based crypto. That is the SAS and LWE problems. And finally, I will give some basics constructions of in lattice-based crypto that can be used from these two problems. Okay, so let us start. Okay, so we all know that cryptography is the science behind information security, and it aims to achieve three main goals: confidentiality, integrity, and authenticity of information. Okay, so historically, so cryptography is, the first form of crypto have been known like more than 2,000 years ago, starting probably with Caesar. So we all now Caesar ciphers, right? Like we have the alphabet of 26 characters and we ship them using the key, which is the ships. Okay, so and for many, many years, so until, I think maybe until World War II, cryptography still remained as an art rather than a science. Okay, so it is sometimes very used in very restricted form in military action, something like this. And but in the last several decades, so cryptography has become a well-studied and very fast developing branch of science. And it's lying in the intersection of mathematics, computer science, and computer engineering. Nowadays, so cryptographic techniques are used ubiquitously everywhere in emails, our mobile phones, computers, social networks, in finance and credit card transactions, in e-commerce, in military communication, and in what is recently we know it's cryptocurrencies. So it's almost everywhere in our digital life nowadays. Okay, so the most basic form of cryptography, so that most of us know, is what is called secret key cryptography, or sometimes it's called symmetric key cryptography. In this basic form of symmetric key cryptography, so we have a sender and a receiver, and they share a secret key. So they somehow agree on a secret key. And the sender can securely send a message M to the receiver in the following way. So because they both know the secret keys, and the sender can encrypt the message M to a ciphertext C using the secret key. And this ciphertext can be transferred over some insecure channel to the receivers, who will use the same secret key to decrypt the ciphertext and obtain the original message M, which we call plain text. Okay, so secret key cryptography in general is very efficient, and in fact it's still the most commonly used cryptographic techniques nowadays, even nowadays. But there's one major disadvantage of this kind of cryptography, because the sender and the receiver have to agree in advance about one secret key. So it's quite inconvenient. So imagine that, okay, so we are in Georgia and our friend is in Bali, so we have to meet somewhere to agree on the key, and then we go back to our city to do the communications. Okay, so it's quite inconvenient. And imagine that we have not just two friends, but we have a lot of friends and friends. So you have to do a lot of kind of private meeting for the key agreement. Okay, so it is quite inconvenient, and for many years, people think that this kind of disadvantage cannot be avoided. Okay. However, in 1976, so there is a major breakthrough in the field made by Diffie and Hellman. So they show that two parties who never met in person in advance can agree on a key. Okay, and they can do communication over insecure channel without meeting in person. Okay, and this work by Diffie and Hellman has essentially established the beginning of what we call public key cryptography. And Diffie and Hellman got a Turing Award for their major breakthrough work. So you know, Turing Award is like the Nobel Prize in computer science. Just 1 year after Diffie and Hellman, so we have the work by Rivest-Rami and Adleman, and who show that we can not only do key exchange, but we can also do encryption and digital signatures using public key techniques. Then what is given, what we use nowadays, we call ISA system, right? And also this work also gave another Turing Award for Rivest-Rami and Adleman. However, from Diffie and Hellman in the next several years, so even though the people have this kind of method to do encryption, signature, and key exchange, but for definition, so no one has a formula of what does it mean for a crypto system to be secure. Okay, so for example, if you have a ciphertext, then what you expect for security of this kind of ciphertext, so you want that given the ciphertext, any attacker cannot recover the plain text, right? But apparently it's not sufficient for security. So what we want maybe more than that. So what happens if the attacker can learn just one bit of the plain text? He cannot recover the whole plain text, but can just learn one bit. And in fact, this kind of intuition does not capture this case. Okay. So what we want is that given the ciphertext, the attacker cannot learn any piece of information about the plain text. But that is just the intuition. It's very hard to capture this by formal definition. And okay, so this hard job was done by Gowasser and Mikali in 1982, so 5 years after ISA. So they give rigorous definition of security for encryption system. So what we call nowadays is semantic security, or okay, so I will talk later. It's called CP8 security for encryption system. And also this work also give another Turing Award for Gowasser and Mikali. Okay, so in public key cryptography, so in contrast to secret key crypto, so we have two keys. a secret key and a public key, and they are mathematically related to each other. Okay, so using these two cases, so we can do some two basic systems, encryption and digital signatures. So for encryption, so we have a sender and a receiver. The receiver just generate a key pair, a public key and a secret key. Of course, he keeps the secret key for himself and just public the public key on his website, say. And then the sender of the message, okay, so he just download the public key of the receiver and use it to encrypt the message. Obtain a ciphertext C and send C over the insecure channel to the receiver, and the receiver can use his secret key to decrypt C 10M. So in this way, so anyone can send, for example, if I publish my public key on my website, so anyone can securely send message to me, okay? Kind of dual form of encryption is digital signature, in which we try to capture the normal handwritten signatures, but in digital form. This one, so one of the operation is kind of inverse. Anyone to sign a message M, so we use our secret key, okay, and we when we sign this message M, so we obtain a signature, say sigma, and anyone who has my public key can verify my signature. So that's basically what we want to capture with of the handwritten signature, right? So without my secret key, no one can generate a signature that is verifiable as is valid. Okay, so you know, because we have a secret key and a public key, so the very basic requirement for security is that given my public key, no one can can compute my secret key, right? And for this, we need some computational assumptions. We need to assume that, okay, it's infeasible for any adversary to compute my secret key given my public key. And you know, currently, the most widely used assumptions in public key cryptos are the integer, the factorization assumption and the discrete assumptions. That is, use some kind of number theory for this. Okay, so basically all of the currently deployed public key system are based on either integer factoring or discrete lot over ellipticals. Okay, so now let me talk about the threat from quantum computers that essentially change the picture of public key cryptography. So in 1994, so Peter Schroeder from MIT, he invented an algorithm on quantum computer that can solve the two problems, integer factoring and the discrete lot problems, within polynomial time. So polynomial time is kind of basic concept in theoretical computer science. So essentially it means that you can, if you are given a very, very powerful quantum computer, then you can efficiently solve the two problems. Okay, so what is the consequence? The consequence is that if one day someone can design and build sufficiently powerful quantum computers, and all of the currently used public key cryptographic techniques will be broken. Okay, so that is a real serious threat. Another algorithm is also related is the Grover algorithm, which was invented 2 years later in 1996. So basically, it's, the Grover algorithm targets not public key crypto techniques, but secret key techniques. So suppose that we have some crypto functions which had n-bit domains. So the security that we expect from this system is that there is no efficient algorithm to invert this one, within the time like ON, okay? But using the groove algorithms, in fact, we can use a quantum computer to do this in time just O of square root of n. So what is the consequence? The consequence is it's not as serious as for public key crypto, as for short algorithm. To thwart the attack from groove algorithm, we can just double the key size. So we increase the domain size to twice. Then in fact, so we can obtain the same security level that we can expect from the original this key size. So is anything clear here? Okay, good. Okay, so let's discuss a little bit more about the threat from quantum computers. So suppose that, okay, so currently we don't know when sufficiently powerful quantum, yes. Okay, so here the size of the domain is n, say, n here may be like 2 to the power 80, okay. So we start with a function of like the secret key content of 80 bits. Then the domain, the whole domain of secret keys will be like header size 2 to the power 80. But the groove algorithm can solve, can invert this function within the time 2 to the power 40. Right? You know, it's square root of this one is 2 to the power 40. And okay, so if you want to achieve 80 bits of security, so we have to double the key size to 160. And then the attacker have to use like algorithm that run in time 2 to the power 80 again. Okay, that's the problem. Okay, so let me get back to this issue. We don't know when sufficiently powerful quantum computer will be available. However, so there are some advancements that made in recent years by IBM, by Google, research so far. Then, okay, so it may be likely that someone may have sufficiently powerful quantum computer, say, in the year of 2030. Okay, so obviously, on the public key cryptography crypto system that we use from that year onwards will be broken, right? But another threat is that if you encrypt something this year, 2019, and we expect to keep the confidentiality of the message for 20 years, okay, so it means that we want to keep the secrecy of the message until the year 2039. But of course, in this case, our message, we do not achieve our goal if someone can come up with some quantum computer before that deadline. Okay. So what does it mean? It means that we have to prepare to find some other technique that can deal with this threat from quantum computer as soon as possible. Okay. So this gives rise of a very major direction in cryptography nowadays, what we call post-quantum cryptography. So in short, post-quantum cryptography refers to algorithms that we believe to be secure in the quantum era. It means that the security of this system must be guaranteed not just against classical computers, but also quantum computers. Okay. So there is related concept, but completely different. It's a quantum cryptography. So quantum cryptography is completely different from post-quantum crypto. So in quantum cryptography, so in fact people use physical property and do cryptography. It has not too much mathematical assumption involved here. Okay, so for designing post-quantum crypto systems, so we have to, we cannot use the traditional assumption from discrete lot and factoring, but we have to use some alternative mathematical foundations. And the foundations that we currently have are from lattices, from coding theory, from solving multivariate equations, and from isogenies of ellipticals and etc. So currently, post-quantum cryptography is the most active research area within the cryptographic research community. So far, so good? Okay. Okay, so in the last decade, so there's a lot of papers working on this field, and just recently, 3 years ago, the American National Institute of Standards and Technology, or NIST, they initiated a process of standardization of post-quantum cryptographic techniques. So they want to, the target is to give a set of recommended post-quantum basic algorithms like signatures and encryption, or a related concept like KEM, or key encapsulation mechanism, that can be used for a long-term future. So that standardization process was announced by NIST in February 2016. And okay, so they call for submission from all of the researchers and implementer engineers in the world. And the deadline was in November 2017. So there was like 82 submissions from all around the world, but only 69 of them are eligible submission, meaning that they meet all of the requirements put forward by NIST. And in January this year, so NIST shortlisted the application after some crypto analytic attempt by the community, and also after some kind of reviews, internal and external reviews. So 26 proposals was invited to submit to the second round, and the submission was done in March this year. And NIST will continue to evaluate, compare all of the submissions, and they expect to have the outcomes within a few years. In any case, so around 2025, so this standardization process will be expected to be complete. Okay, so at that point we will have a new set of recommendations for public key cryptography that can be used in the quantum era. Okay, so let me dig down a little bit to the 26 second round proposal to the NIST process. So by primitives, so among the 26 proposals, we have 17 encryption or KEM, and 9 signatures. Okay, so and by assumptions, so for lattices we have 9 encryption and 3 signatures. From codes, we have 7 encryption system and no signatures. And from hash functions, so there's one proposal for signatures. There are also 4 signature proposals from assumption in Solvin various systems. 1 encryption or KEM system from isogenies, and 1 signatures from zero-knowledge protocol. So it's kind of advanced concepts that can be used to design digital signatures. Okay, so we can observe from this. So 12, so 9 plus 3, so 12 proposals are from lattices. So lattice, in fact, is the major tool for, yes. In fact, for building hash-based signature, so there is some way to do it. Okay, so given a hash functions, in fact, you can build a one-way function, and from one-way function you can build digital signatures. But we don't know how to build encryption from hash. So, in fact, generically, to obtain a secure encryption system, we require a stronger assumption than collision system of hash. Okay, so for signature building from hash, in fact, it gives a very well-studied security properties. Okay, so NIST, I think it's in favor of this one, but the disadvantage is that the signature size is very long, much longer than what you can obtain from Lattice, for example. But the security proof for hash-based signature is normally very well understood, easy to understand, and the assumption is, in fact, just say SHA-3 is secure. Yes, so it's more study than other mathematical stuff here. Also, just my observation is that when NIST selected candidates for the second round, so they want to keep the diversity. So they want to take, because there's no obvious attack on this kind of primitive, so they just want to get a diverse assumptions to the second round. But eventually, I don't know what they will recommend. But for sure, a few Lattice based system will be eventually selected. Okay, so now let me talk about Lattice-based crypto. So Lattice, in short, are discrete subgroups of R to the M. So the m-dimensional space of the rules. So before, okay, so we can divide the history of Lattice-based crypto into a few major periods. So before 1996, okay, so like 200 years ago, people already started to use Lattice as a tool in number theory. So some of the prominent names include Gauss, Lagrange, Minkowski, et al. And from the 18th to early 20th century, it's just a tool in the what we call the geometry of numbers. A breakthrough of in this field were given by Lenstra, and Lovaas in 1982. So what they invented what we call nowadays a LLL algorithm. So it is a basic reduction algorithm. So given a basic of the lattice that is very long, so they obtain a somewhat shorter basics in polynomial time, and the main utilities of the LLL algorithm is for not for building crypto but for breaking. Okay, so so there are some examples of using LLL to break some crypto systems like the Merkle-Hellman crypto system and some weak form of RSA, for example. Till 1996, so the main use of Lattice in cryptology is just for breaking. But a breakthrough was given by Einstein in 1996, where he showed that Lattice can also be used for building secure crypto system. So what he showed is that there is a so-called worst case to average calculation for Lattice problem. And based on these results, so he can build the very basic crypto primitive, which is a one-way function, on the harness of lattice problems. So what he saw is that there is a problem called SIH, which is at least as hard as lattice problem in the worst case. Meaning that okay, so in crypto, so normally we generate some random instant when we generate a key pair. So basically we have some randomness there, right? So what we generate is a random instance of the problem, and the hardness of this one is referred to as average case. And what Anta shows is that this kind of problem, SIS, is at least as hard as lattice problem in the worst case for any lattice. And based on this problem, he can build cryptographic one-way function, which is the basic for building more advanced systems. So more concretely, so what Anta shows is that if there exists an efficient algorithm solving a random instance of this problem, then there exists an efficient algorithm solving some lattice problem on any lattices. So the word random here refers to average case harness, and the word any here refers to worst case harness. Okay, it's very, very strong security guarantee. Suppose that there exists some instance of lattice problem that is hard, then the problem, the SS problem is also hard. Okay. Is any question here? Okay, so let me move a little bit. So after the work of Einstein until 2005, there's some subsequent work that gives some improvement. For example, the work by Einstein, the work in 1997, so that just one-way function can be obtained from lattice, but also public key encryption. However, their original system is quite complicated and very inefficient, so mostly of theoretical interest. In 1998, so a group of researchers invented what we call nowadays N-True, which is, also provides public key encryption and signatures. They are quite efficient, but in fact the N2 system initially did not have the strong evidence of security, meaning that they don't have the same security guarantee like Einstein's approach. And in fact, several variations of N2 signatures were so insecure just very quickly. We should also mention the words by Regev and Michancio, who give us some great simplification and improvement of earlier theoretical works, and they obtain stronger security and better efficiency for the previous work. And the breakthrough was done in the year 2005 by Regev, who introduced a famous problem nowadays called the learning with errors problem, or LWE. So currently, maybe when we talk about lattice-based cryptos, then you can imagine that 90% of them are related to LWE problems. So, okay, so Regev result is similar to Einstein's in this sense that he showed that if there exists some efficient algorithm solving a random instance of this LWE problem, then there exists a quantum algorithm solving lattice problem on any lattices. So basically, LWE is at least as hard as lattice problem. Okay, but except for the two keywords random and any here, there is another word that is highlighted here, quantum. Okay, so what does it mean? It means that, so here now we call this quantum reduction, okay? So this will in fact some disadvantage of this reduction. Why? Because anti-reduction, so that if we have an efficient algorithm solving SAS, then we have an efficient classical algorithm solving lattice problem. But here, the results only say that if we have efficient algorithm solving LWE, then there is efficient quantum algorithm solving lattice problem. Then it means that the assumption here is stronger in the sense that it's more likely that we will have a quantum algorithm solving lattice problems than a classical algorithm. So there are many follow-up work trying to remove this quantum in the reduction. So if we can remove this quantum word in this reduction, so we obtain a better harness result. Is it hard to understand? So here it means that we have to base the security of our system on the assumption that there does not exist any quantum algorithm solving the lattice problem. Okay? And it is stronger than the assumption that there exists any algorithm solving the lattice problem. And the introduction of the LWE problem led to various crypto systems, mostly for encryption primitives, and led to the explosion of lattice-based crypto. So now from 2005 to present, so there are like maybe more than 2,000 follow-up work after RegF. So let me briefly review some of the important work. The first one I would like to mention is the one by Juli, Packard, and Vaikunthanathan. So they give a rich technical toolbox for lattice-based crypto. So they show that based on lattice problems, we can obtain more advanced primitives like trapdoors, also trapdoor-based signatures, and what we call identity-based encryption, which is a high-level advanced crypto primitive. And the work by Juli in 2009, so he showed that based on some form of lattice problem, we can design what we call a fully homomorphic encryption, or FHE, which is a very long-standing problem in the whole cryptography. So fully homomorphic encryption means that allow us to compute on the ciphertext. For example, you want to have you encrypt some your plaintext, and you want to evaluate a function on your plaintext. So one way to do that is you decrypt everything, you evaluate the function, and then you encrypt the result. But fully homomorphic encryption allows us to perform on of the computation on the ciphertext. So thanks to this property, so we can delegate on of the computation to some server, some cloud, for example, and the cloud. So what we can do is that we encrypt our plaintext, give it to the cloud evaluate the function and give the result of computation, which is a ciphertext back to us, and we just decrypt and obtain the result of computation. So it's very powerful primitive, and have a lot of applications. Also, from 2005, there are many other theoretical advancements. So people show that we can also build high-level encryption system like attribute-based encryption, functional encryption, also what we call group signatures, electronic cache system, and so on. Another direction is to improve the efficiency of existing system, and there are also many advancements in this line of research, and people can obtain efficient variant of SS and LWE and give a better trapdoors and shorter signatures, more efficient encryption system, and so on. So currently, I would say that lattice-based crypto is a mainstream research direction. And just based on my personal observations, that if you pick a random cryptographer, then the chance that he has been working on lattice-based crypto or he's interested in doing this is more than 50%. Okay, so that gives you an impression of how popular is it is lattice-based crypto nowadays. Okay, so let me review the advantage of lattice-based crypto. Why is it so popular? Why is it so attractive? First, let me mention the conjecture post-quantum security. Okay, so despite many attempts to attack lattice problems, so currently all of the known classical algorithms for solving lattice problem requires running time sub-exponential in this lattice dimension. This means that currently we don't know any efficient algorithm run on classical computer that can solve lattice problems. And we don't even know any quantum algorithm that performs considerably better than classical ones. This means that, okay, so there are also some attempt to use quantum computer. So assume that we have quantum computer. What can we do with lattice problems? Many attempt to do that, but there's no significant success so far. In fact, Peter Shaw himself also gave an attempt a few years ago. So he uploaded his paper on arXiv, and it was quickly identified by the community that is flawed, and he have to withdraw his paper. So so we can have a strong belief that lattice problem can resist against quantum computers. And also, we have what I just mentioned previously, the security guarantee from worst-case harness. That is also a very unique property. So in short, we can prove that some lattice-based cryptographic constructions are infeasible to break unless all instances of certain lattice problems are easy to solve. Just assume one of them is hard, then lattice-based crypto is secure. So that's the what is called the worst case to average case reduction. Also, another advantage is that if you look at number theoretic cryptography based on discrete lot and RSA and factoring, so normally we have to do some kind of exponentiation operation, which is quite costly. In contrast, in lattice-based cryptography, so we mainly deal with addition and multiplication over some ring ZQ for a relatively small Q. So the Q that we use in lattice-based crypto is quite small compared with Q that we use in or the P, the prime P we use in discrete lots. So the Q here is maybe just like a range from 2 to the power 10 to 2 to the power 30 for most of the crypto system. But the Q, you know, the Q in discrete lot symbol, it must be 2 to the power 240. Okay, so asymptotically, so lattice-based crypto system are simple, efficient, and can be parallelized. It's okay? Okay, thanks. Also, from the theoretical aspect, based on lattice, we can also build not just basic system, but also very powerful constructions that were not known to be achievable under the classical assumption, under the discrete lot and factoring, for example, FHE and functional encryption. Okay, so this is a short summary of it's just a picture that I try to capture what happened in lattice-based crypto. So basically, we start with the lattice problem with the foundation for harness, and based on lattice problem, we can obtain two families, SAS family and LWE family. So the two, we can divide this way. Some family of crypto system that based on SAS and some based on LWE. And from this we can obtain basic system based on SAS and basic system based on LWE. From SAS, for example, one-way functions, commitment schemes, signatures. From LWE we can obtain encryptions and other advanced encryption system. There are also some more sophisticated system like that require the combination of the both families, the two families together with other techniques like what you know, the zero knowledge proof and so on, and it gives us a more advanced system on top of the basic system. For example, the privacy preserving construction that you require not just the security but also the privacy of user, the anonymity of user among some population. So that requires the combination of the two families together with additional extra dedicated techniques. Okay, so in the two lectures, I just try to cover the first part of this, maybe the left hand side of the picture. So from lattice problem, how we obtain the SS family, how we obtain the FW family, and how can we put a simple basic crypto system from these two problems. Okay, so let us start with the technical part. Okay, so we talk about lattice a lot, but what is lattice formally? It is okay. So it's one definition. An n-dimensional lattice L is any subset of the space R to the n that is both that have two properties. First, it is an additive subgroup of R to the n, meaning that the zero vector belongs to the lattice. And for every x and y belonging to the lattice, then minus x and x plus y also belong to the lattice. And it's discrete. Okay, so you know that the whole set R to the n is not discrete, but this subgroup must be discrete, meaning that for every x inside belonging to the lattice, there is a neighborhood in R to the n in which x is the only lattice point. Okay. So what does it mean? So you know the neighborhood is if we take a very small epsilon, so we can take a neighborhood in which this is the only lattice point. It means that it is discrete. It's not a continuous in the sense of calculus, right? So okay, so there is an epsilon positive such that any two distinct lattice points x and y are at distance at least epsilon. Okay, you take so there exists some epsilon such that we take any two lattice points, then their distance must be at least must be bigger than epsilon. So it means that the set that we are working on is discrete, it's not continuous. Okay, so okay, let's consider several examples of lattice. Okay, so you see, okay, the question is whether the singleton set that consists only of the zero vector is a lattice or not. Yes or no? Yes, it's a lattice, right? It's a satisfied honorable property, so it's a discrete. It's a subgroup of R to the n, and of course it's a discrete, only one element. How about Q to the n? Yes or no? Is it a subgroup of R to the n? Yes, right, obviously. But is it discrete? No, it's a subgroup of, it's not discrete, so it's not a lattice. How about the set Z to the n? Yes, right, it's a subgroup, and you know the integers are just discrete. Yes. And the scaling, let's say we have to take a lattice L and a real number C, then whether the question is whether the scaling CL, which is the setup on C times X for on X in L, is it a lattice? Yes, it's a lattice because it just scale is bigger. And one example is the even integers. Okay, so the setup on even is a lattice in dimension 1. And how about the setup on odd integers? Why? Yeah, it's a discrete, but not a subgroup, right, of the whole set. Yes, they do not form a subgroup of R. And However, it's comprised a co-set of the lattice 2Z that we consider in the previous example. Okay, so now let us go to the basic definition in lattice. So one of the concepts is what we call the successive minima. Okay, so for any lattice, we can define the minimum distance. Okay, it is essentially the length of the shortest non-zero vector in the lattice. Okay, so what we know here by lambda 1 of L is the minimum of on V, where V is a lattice that is non-zero. We can always define that because we work with a discrete set, right? So more generally, we can define the ith successive minimum lambda I of L, which is the smallest real number R, such that R has I linearly independent vectors of norm S mod R. Okay, so in the picture here, so if you take this one, here is the sphere of radius lambda 1 here. So this one is the length here is the first minimum, and you look at the second vector that is non-zero and not linearly independent from this one. So it's essentially with this sphere, and the radius of this sphere is what they call the second minimum. Okay, so here we can consider the norm is the Euclidean norm L2, but in general, successive minima can be defined with respect to other norms, and the most commonly used maybe L infinity, the infinity norm. So we can, if a lattice of dimension n, so we can define n successive minima this way. Another equivalent definition of lattice in terms of linear algebra. Okay, so every non-trivial lattice L is in fact it is infinite, but it is finitely generated as the integer linear combination of some linearly independent basic vectors. So more formally, suppose that B, matrix B, whose columns are B1 and Bk, each of them is a vector in dimension n. So we have a matrix B here in R to the n time k, consisting of linearly independent vectors in R to the n. And the lattice generated by this matrix B or the basis B is the set of integer linear combinations of the basis vectors. Okay, so it's the set on vector of the form B times Z, where Z is a vector in integer vector of dimension B. So here on the picture on the right hand side, so here this is the lattice in the dimension 2, and B1, B2 form a basis for this lattice. So they are linearly independent, and they generate the whole lattice. In this definition, the integer k is called the rank of the lattice. So in lattice-based crypto, so we only work with full rank lattices, meaning that k equal to n. And one remark here is that for a given lattice, there are many basics. In fact, the basic is not unique. For example, for this example lattices, so these two vectors, the small vector, also form a basic for a lattice. So there are in fact infinitely many of them. Any question? Okay, so one remark here is that it's different from the concept of vector space. Okay, so for vector space, in fact, we don't require this Zi, this like the coefficient in the linear combination to be integers. For vector space, it can be real from here, but we work only with integer combinations. So this is the lattice. Okay, so now let's talk about the computational problems that can be defined over lattices, and that are conjectured to be hard despite many efforts from the community. The most well-studied computational problem on lattices, maybe you already heard about this, is what is called shortest problem. So what is it? So given a lattice L with a basis B, the problem asks to find the shortest non-zero vector in the lattice. So which means a vector V in the lattice, so that the norm of V is exactly the first minimum, lambda 1 of L. Okay. In one-dimension lattice, so it's very easy to find this one. But if the dimension increase, the dimension of lattice increase, so it becomes gradually difficult. And when n is big enough, like the 256 or 512, then the problem becomes extremely hard. In fact, this problem is hard, but it is not really useful for cryptography. And important for lattice-based crypto is what we call the approximation problems. Because you know that the SVP problem is for very big dimensions. In fact, we cannot solve it, and we cannot use it to build cryptography either. And the approximation problem is some kind of relaxed version of exact problem. So they are parameterized by some function gamma of the dimension of the lattice, and gamma is bigger than at least 1. And the approximation version of SVP is as follows. So we call the SVP gamma. So also given a lattice, but now the problem asks to find some vector V non-zero such that the norm of V is at most gamma times shortest vector in the lattice. So this is a relaxed version. It's still hard, but it's easier than the exact version. So basically, now it's asking you to find a vector that is slightly longer than the shortest vector. If gamma increase, the problem becomes easier and easier. Any question? Okay. Also, important problem in the lattice is we call the SIVP gamma. This is a search problem that related to the nth successive minimum. So the problem is as follows. Given a basic B of a full rank n-dimensional lattice L, the problem asks to output a set S consisting of on the SI, S1 to Sn, of n linearly independent lattice vector, where for every I, so the norm of the vector Si is mo gamma times I think here is just lambda I of L. Okay, sorry, it's the typo here. So basically, it acts to find a set of n linearly independent vectors. Each of them is slightly longer than the ith minimum. So another famous problem we can define lattice is the closest vector problem. So here I introduced the promised version, which is called the bounded distance decoding, or BDD. Also, this approximate version. So given a basic B of a lattice L, and we have some target vector in the space, say T. But we have the guarantee that this T, the distance from this T to the lattice is is less than some D, which is equal to lambda 1 divided by 2 times the gamma. And okay, this guarantee this says that there is some unique vector, okay, v, such that the distance between t and there's some vector v in the lattice such that the distance from t to v is less than d, right? There's only one vector satisfying this property, and the problem asks to find that unique vector. Okay, so we reviewed the sorted vector problem, the approximation of the problem, and SIVP and PDD as well. So in general, so the problem are somewhat equivalent in the sense that they reduce to each other. Okay, so let me review the complexity of lattice problem, meaning the harness results, how hard they are based on the existing our current knowledge. Okay, so for the factor, okay, so here the factor gamma will increase. So you know that when gamma, the approximation factor gamma increase, the problem become easier, right? But for very small gamma, like gamma from 1 to square root of n, then we know that the problem are NP-hard. So I hope that you are familiar with the concept of NP-hardness. Okay, so NP-hard means that it's belong to the class of the most difficult problem that we have, and we building cryptography from NP-hard problem is currently an open problem. Okay, so it means that for this range of gamma, we know that the problem are extremely hard, but we don't know how to build crypto. So it's very hard, but it's not useful currently. For gamma that is larger than square root of n, then the problem are unlikely to be NP-hard. Okay, so it means that are slightly easier. And for gamma, which is polynomial in n, the dimension of lattice, then the best known algorithm or even quantum algorithm required exponential time and space in dimension. Here we have used the notation 2 to the theta of n, so to denote the exponential time and space. So it means that the problem still remain hard for polynomial gamma. However, when gamma increase to this kind of level, which is slightly sub-exponential, so 2 to the power theta of n log n over log n. So it's less than theta of n, right? Asymptotically, so it's slightly sub-exponential. Then we know some classical algorithm that, for example, LLL, the one the Lenstein-Lovász lattice reduction, and some of its improved variants that can solve lattice problem for the parameter gamma within polynomial time. So what does it mean? It means that if we work with a very, very big gamma, then the problem is easy. Okay, and we also cannot do crypto with the easy problem as well. Okay, so in lattice-based crypto, so we deal with the gamma that is, of course, cannot be too small. Too small is very hard but not useful, and cannot be too large, right? Too large, so it is not high anymore. So we work with gamma range from theta of n to that is upper bound by some polynomial function of n. And normally we work with for basic system, so we can work. We normally work with gamma around n to the power 5. For some other advanced system like fully homomorphic encryption or functional encryption, attribute-based encryption, and so on, we can work with more with larger gamma, like a bigger polynomial, or it can be super polynomial, but still not exponential. Yes, and for the kind of advanced construction like fully homomorphic encryption, PRF, which is a pseudo-random function, functional encryption, then the factor is super polynomial. It means that gamma is run faster than any polynomial function. It's increased faster. And in these cases, we have to rely on the assumption that the lattice problem still have for kind of level of gamma, and the assumptions are strong assumptions. Okay, so when you read a research paper in crypto, so there is a confusing concept here. Strong security means good, right? But strong assumption is mean bad. Okay, so if someone say that, okay, my system rely on a weaker assumption, in fact, it's a good thing. Strong assumption, for example, in this case, if for example, to construct this, say, this functional encryption, we rely on the assumption that SIVP is half for gamma equal to n to the power 100. Okay, so this assumption is strong because it's more likely that there is some algorithm solving this lattice problem with this big gamma. And if we just rely on the assumption that gamma is somewhere less than n to the power 5, then it's a weaker assumption. It's more reliable assumption. So weaker is mean more reliable, and stronger is mean worse. Okay, so just a remark when you read papers. Okay, so now let me go to the two problems, SS and LWE, which are providing that lattice problem also hard. So in fact, when you read papers, or you you read paper in lattice-based crypto, and also in popular media, for example. So normally we just see the SS and LWE problem. We don't really see the lattices because they have the 100 guarantee from lattice problem, and they serve as the basis for building lattice-based cryptos. In fact, they lie somewhere in the between, right? And the problem, in fact, is not as complicated as geometric problem from lattices like SVP, SIVP, BDD, so on. In fact, they just deal with matrix and vectors over some ZQ. Okay, so let me go with SS and its harness. So you see a definition of SS problem. So we work with 4 parameters: positive integer n, positive integer q, and m, and a real number beta. And here is the main parameter. So you can think of it as the dimension of the underlying lattice in the lattice problem. So in practice, we need to work with a very big n, like 2 to 256. Okay, for smaller n, so the underlying problem is easier. So this is the main security parameter. It means that if we want more security, we increase it n. So n and q, we define additive finite group zq to zn. Okay, so it's the group of vectors n over zq. And m is the number of the group elements. And some beta is the bound. It's less than q. The problem is as follows. Given m uniformly random vector a1 to am, each of them is a vector in the q to the n. You can form the matrix A, right, in the q to the n times m, consisting of m columns. Each of them is ai. The problem asks to find a non-zero integer vector x in of dimension m, such that the norm here, the norm of x is less than beta, and a times x equal to 0. So it means that the linear combination of all of the column AI with coefficient xi is 0. And of course, we have to exclude the trivial case where all of the xi are 0. So the problem asks to find a non-zero vector x. And here the norm can be defined with respect to any LP norm, in fact. And typically we work with L2 and the infinity norm. So in the following we will address the only the Euclidean norm. Okay, so basically it acts to solve a system of modular linear equations. It's very simple, very linear algebra. Given A, uniformly random, find some x that is somewhat small in integer such that A times x equal to 0. In matrix vector form it's like this. So we have a matrix A here and vector 0 here. Find some non-zero x, vector integer vectors such that A times x equal to 0. Okay. Of course, we have to set parameters so that the problem is hard. Okay, so let's consider some facts on the hardness of this problem with respect to the 4 parameter n, m, q, and beta. Okay, so first, okay, just given n and q and parameter, we have to set the m and beta such that the problem is guaranteed to have a solution, right? If the problem is not guaranteed to have a solution, then the problem becomes meaningless, right? It must have a solution, and finding the solution must be hard. Okay, so how to do that? Suppose that we, okay, so let's consider this set of parameters. N 256, Q is 1024, M is 2561, and beta is 60. Can we guarantee that the problem, SF problem with the parameter have a solution? So not really intuitively, right? Okay, so let me try to write on the board. So it's a simple pigeonhole argument. So if we consider a function f(a), so given our matrix A, consider function f(a) that mapped 0, 1 to the m to the q to the n. Okay. Then suppose that 2 to the m is bigger than, I suppose that this domain is bigger than the range. The size of the domain is bigger than the size of the range. So 2 to the m, this domain has size 2 to the m, and this range has size q to the n. I suppose that this condition is satisfied. Okay. So now by the pigeonhole principle, so we have a more pigeons than holes, right? So we can find some x1 and x2 such that f(a) of x1 equal to f(a) of, okay, so sorry, I haven't defined f(a)s. Okay, so it for x in 0, 1 to the m, so it maps it just to a times x mod q. Okay, so by the pigeonhole principle, so we can find x1 and x2 that are distinct, such that f(a) of x1 equal to f(a) of x2. Okay, so it means that a times x1 equal to a times x2 mod q, and we can transform it to a times x1 minus x2 equal to 0 mod q, right? Very simple. And because x1 and x2 are distinct, then this vector is non-zero. And each of them belong to the set 0, 1 to the m. Then we just call it like x is the difference, x1 and x2. Then this x is, on the one hand, is non-zero. On the other hand, it must belong to the set minus 1, 0, 1 to the m, right? And you know the norm of this one is, because the Euclidean norm is, in fact, it's bounded by square root of m, right? Because it's dimension m, and all of the coefficients are belong to the set minus 1, 0, and 1. And if we set parameter like this, and beta is like this, at least square root of m, in fact, we guarantee a solution. We guarantee that the problem have a solution, right? Because now we have a times this x equal to 0, and x is non-zero itself. Okay. So you can verify that our parameter satisfy this one. So here q is 2 to the power 10, and q to the n is like okay. So we can verify that 2 to the m is bigger than q to the n, and beta here is 60 is at least square root of m. So you know 60 is bigger than square root of the 2561, right? And in general, a typical setting for the parameter must be like m is bigger than n log q, because 2 to the m, you take the log of that inequality, two sides of the inequality, so you have m is bigger than log n times log 2 of q, and beta is bigger than square root of m. And with this setting, so we guarantee that the problem have solution. Okay, so my second question is that without the restriction of the norm, the norm of x is at most beta, so what will go wrong? Is the problem meaningful if we don't restrict the norm of the solution? You know, here, in fact, we work with an, you know, if m here is bigger than n log q, right? It means that we have more equation. No, we have more variables than equations, right? So in fact, this system, if we don't restrict the norm of x, so it's very easy to solve. For example, you can use Gaussian elimination, right, to solve the system. It's very efficient. So the problem only meaningful if we restrict the norm of x. So finding an arbitrary solution of this system is in fact easy. And we want that finding a small solution is hard. That justifies the name of the problem. In fact, SSE, short integer vector problem. Short integer solution problem. Okay. So the problem will be trivially easy if we don't restrict the norm. At least we must set that beta is less than q. Why? Okay, so there is a trivial solution. Okay, if you know that this equation is mod q, right? So if you just put the first coordinate of x to be q and everything else be 0, so it's also a non-zero solution, right? And with norm q. So this is, if we set beta equal to q, for example, then the problem is also easy to solve. So we have to set beta less than q. In fact, in practice, most of the time we will have to set beta much smaller than q to guarantee the hardness of the problems. The smaller beta, the harder the problem is. But beta cannot be too small. For example, if it is smaller than square root of m, then we can no longer guarantee that the problem has solution. So we work with small beta, but not too small. Okay. Okay. So another question is that if we keep n, m, and q, and we decrease beta, then we will get an easier or harder problem. I just mentioned this. So we keep on the 3 parameter here, and we decrease the norm of the solution. In fact, we get a harder problem, right? And once beta go down 2 levels, square root of n, in fact, the problem is impossible to solve because there's no guarantee that we have a solution, right? Okay, so now another question is that if we keep n, q, and beta, and we increase m, so the problem become easier or harder? What do you think? So, yeah, just discuss. Okay, we keep this number of rows. We keep the modulus q. We keep the norm beta, but we increase the number of columns. It's become harder. Okay, and so who thinks it will be harder? And who thinks it will become easier? Okay, so sorry. Yes, yeah, exactly. In fact, it doesn't become harder. Okay, in fact, you can see that it become. I mean, if we say easier is maybe not really rigorous, but you can think this way. I have here m originally I have m columns, right? Now I add one more column. I increase m one more column, and I add 1 0 here, the last one. So we have a m plus 1 dimensional vector, which is the original x plus 1 at the end. So in fact, it is a solution to the new problem, right? So in fact, if we can solve the problem with dimension m, with m columns, then we can also solve the problem with m plus 1 column. Because this one is, we still have it like add 1 column and add 0 here, we still have a prime times x prime equal to 0, and x prime is non-zero, right? Because the original x is non-zero. So if we can solve the problem with smaller dimension, we can solve it with a higher dimension. So the problem doesn't become harder. So we can say that it becomes easier. If we can solve this and we can solve that. So another question is, if we keep m number of column and modulus q and the bound beta, but we increase n, so how the problem will become? So now we keep this one, but we increase, we add some rows here. So the matrix become fatter. It become easier or harder? You see, if we have the x such that A prime here, the factor matrix, times x equal to 0, then we can deduce that the original matrix multiply x also 0, right? But the inverse is not necessarily true. So in fact, we can say that for bigger n, the problem is harder. That is true because you know n here is the, as I mentioned previously, n is the major security parameter. It related to the dimension of some underlying lattice problem. So for lattice with higher dimension, problem is expected to be harder. Okay, so we have still 5 minutes for this session. So let me state the harness results that obtained by. Okay. Okay. So now. Okay. So we talk about the SS problem, which is defined in terms of linear algebra, right? So how is it related to lattices? Okay. So one way to interpret the relation between SS and lattice is the following way. So we can consider what is called the QRE lattices. So for any matrix A in the Q to the n times m, we can define this set L bot A, which is the setup on X in Z to the m, set up A times X equal to 0 mod Q. Is it a lattice? Of course, you can guess that it's a lattice. We will talk about QRE lattice. So, but why? Okay, so we can use the first definition of lattice to verify this. Is it a subgroup of Z to the m? Yes, right. Because we know 0 belongs to this one. Because you know A times 0 equal to 0, and it's if X belongs to this set, then minus X also belongs to this set, because A times X equal to 0, meaning that A times minus X equal to 0. And if A times X equal to 0, A times Y equal to 0, then A times X plus Y also 0. Right? And so it's a subgroup of G to the M, and it's a discrete, obviously. So it's a lattice. Okay. So now you can find the relation between this one and the SS problem that we defined previously. In fact, the problem here, SS problem, acts to find sufficiently short vector in this lattice L bottom A for uniformly random A, matrix A. So we can view this one as an average K short vector problem on this family of QRE lattices. Average K means that because we just generated A uniformly random, we act to find a reasonably short vector in this lattice, which is non-zero. So this is the one connection of this problem with lattices. Okay, so so to conclude this, the first part of the lecture, so let me recall the harness results, which is called the worst case to average reduction for SAS. So this one was first obtained by Einstein and improved in various subsequent works. So this theorem says that for any polynomial m in the dimension in n is security parameter here, and any beta positive, and any sufficiently large q, then solving the SAS problem with the parameter n, q, and beta with non-negligible probability is at least at solving lattice problem SVP, SIVP on n-dimensional lattices with with overwhelming probability, and for some beta equal to some gamma equal to beta times a small function in n. Okay, if it's too hard, then what you can take away from this is that solving SAS is at least as hard as solving a lattice problem. You take uniformly random matrix A, you define the problem with the parameters, and you can guarantee that this problem is hard, assuming that lattice problem is also hard. Okay. So here are some remark on the theorem. So n is the dimension of the worst case lattice problem. So in fact, if n increase, then the problem become harder, as we observed in the previous slide. And if beta increase, so you can see that beta increase and this gamma also increase, right? Then the problem become easier, because gamma increase and lattice problem is also becomes easier, and because we have the SAS to this reduction from this one to this one, then the problem also become easier. And parameter m, if it's large enough, then in fact it essentially has no effect in the reduction. That's the one observation. Okay, so let's continue after the break. Thank you.
Thank you very much for the lecture on Introduction to Lattice-based Cryptography. Dr. Khoa Nguyen from Nanyang Technology University. Let's give him applause once more. Okay, it was the presentation, but part 1, yes? Okay. We will continue to the next part after a 30 minutes coffee break. Let's enjoy your time. Thank you.